Okay, I'm screwing around with some of this stuff on Falstad, just trying to look at the the basics of inductors and stuff, and it's pretty interesting. But understand this about inductors, though, everything boils around energy. But the stronger the current you've got flowing through an inductor, the larger the amount of energy you'll store inside the inductor. But as a result of that, its charging rate is actually the opposite of what you would think. At any rate, the amount of energy stored in an inductor is 1/2, Li squared. So keep that in mind. And the voltage is, of course, proportional to di dt equal. But right now, let me reset this. Okay. Right now you can see, I've got a transformer here, and in fact, this transformer modeled in this program, they're both set to 1 Henry, but it does actually behave with no load. It behaves just like this. It's identical. So, this is basically, from this inductor, and then this stuff over here applies to this one. And then here, this applies to the capacitor, this applies to that inductor, and this applies to that resistor. But at any rate, if I charge both of these up, you can see your curve here, and these are 5 volt supplies, by the way. So it starts at 5 volts, and you can see the voltage drop across it as the field starts to charge up. Now, what's interesting is to note the difference between this charge curve and this charge curve. Because remember, inductance-wise, these are the same. They have the same resistors. Okay, but because I got a capacitor in this, and a pretty big one, a 10 millifarad capacitor, that's why it has this rather unusual charge curve. But, you can kind of look at the voltages. They're not really all that large. But again, we're getting oscillation out of it just simply because we're charging it, so it's also trying to charge the capacitor, but it's basically a tank circuit here that we're inductively stimulating with a pulse, our charging pulse. But like I said, you can see oscillations in it. I don't know. So this is at 76 millivolts, so you're not seeing much in the way of voltage, on the our voltmeter here is not really measuring much in the way of a wave, but in the current you can see a waveform here, just like you can in the capacitor. I mean, that's definitely got something going on between it and this coil. I don't know how accurate this is, but this is just something I'm curious about to try it with capacitors and inductors. And we'll get to resistors, in a while. But at any rate, let's go ahead and dump this charge because the field is fully charged up. Now you can see what the current just plummeted here. Much the same over here. The current dropped precipitously, and you can see the voltage is really high, in this circuit. When we discharged it, but note it's going through a 1K resistor versus a 10 ohm resistor to charge it. So that's something to keep in mind. But it's a matter of the energy you store here. Meantime, the capacitor part, you can see that our voltage on the primary, we got fluctuations. The current is pretty stable from the looks of it. Because it's like 1/2 amp. But now we're getting kind of a reading, so you can see the fluctuations here, but it's not very much. It's pretty low current at this point. But basically, you know, this is from this wire we're getting this reading, so you can see eventually what's happening is this resistor is going to dissipate this energy from this resonant tank through the inductor, but it'll take a while because this is so big. So, you know, I have no idea how long it'll take, you know, with the oscillations. Again, with such a big capacitor and a big inductor, because 1 Henry is a big inductor. Okay, but just realize that, you know, it's going to fluctuate, but it's only 5 volts. You know, we're only getting plus or minus 5 volts roughly on these oscillations. But again, that has a lot to do with this being such a big capacitor. So, but rather than sit here and wait for it to run out of juice, I'll switch it back to what it originally was, which was 10 microfarad. Okay, now let's give it a whack, charge it up. So, you know, you can see the capacitors, you know, from that whack, you know, went up to 8 volts, and you can see the oscillation in here on the current too, and even on the voltage you can see there was a little bit of a hit. But overall, you know, our max current is going to be about 1/2 amp with a 10 ohm resistor there. So, you know, but this thing is almost charged up fully now. And like I said, you can see the curves look similar at this point because, again, it's a much smaller capacitor. You know, you don't see as much of a deformation taking place here. But, you know, we're getting pretty low at 1 millivolt. You know, you can see that over here, you know, this is converging to a point. So let's give it a whack. Alright, so now you can see the oscillation taking place, and, you know, we're talking 76 volts versus 125 volts here, and then even here you got 427 volts versus 75 volts. So, I mean, it definitely has a huge impact, you know, on what goes on in the primary. So if you had some sensitive circuit here, you know, it would be getting whacked by some really huge voltages because of this. So, and you can see, you know, the current waveform over here too, you know, oscillated a bit when it hit the ground. So, you know, that's basically what goes on with that. Now let's go ahead and charge this up again. Now I'm going to lower the impedances down to 100 that we're dumping these inductors through. Okay, wait for it to charge here because we're still charging with a very low resistor. So it's got a lot more energy in it. Remember, it's going at the 1/2 amp, so it's, you know, 1 Henry times, or 1/2 Henry times, you know, 0.5 squared basically. So that's how much energy it's got in. Anyway, let's give it a whack. You can see what happens. Okay, the current drops much more slowly now. You know, and the voltage difference is not nearly as high. And the same thing kind of applies to this. You know, this damped out really quick. I mean, we saw a little blip here because of that capacitance, but again, it was nothing like it was before. I mean, you know, there's certainly a little oddball kind of waveform here, but overall it dissipated that pretty damn quick, and that's because we had a smaller resistor here. But again, it took longer to discharge it over on this circuit, and even on this it took longer than before, even though we lowered the resistance. But remember, the voltage wasn't nearly as high. Now, if these had the same resistance as each other as our charging circuit, well, here, yeah, if they had the same resistance. Now let's give it a whack. Okay, so you can see just like before, you know, or our capacitor is hiccuping a little bit, you know, as it tries to charge up. We've got 5 volts here, 5 volts here, whatnot. And then here this is up to 8 volts, so it's a little higher. Like I said, we're about charged up. You know, you can see we've got only about 60 millivolts across it now. Because remember, once you get one of these inductors fully charged up, you know, it has maximum current through it. It has 0 voltage across it, but it's got maximum energy stored in the field. So then when you dump it, it generates, you know, by switching it, it generates an electric field substantial enough to try to maintain that current. But it flips its polarity when it does it. So anyway, let's give it a whack. Okay, so right now you're seeing a real quick and dirty oscillation here, but you know, it's falling off really quick. You know, it's not resonating or, you know, acting like a tank circuit as much as it did. So, but that's because we got such a low impedance now, it actually quickly dampens that oscillation. So even though the higher impedance produced a much higher voltage, but the fact of the matter is that, you know, you can see here, you know, that the voltages aren't nearly as high. I mean, even this only has, guess what, maximum of -5 volts. So when we go charge it again, this is still acting exactly the same. Again, it's quickly damped because of the relative size of the capacitor versus our load. But again, you're only seeing like 5 volts, you know, on this side, 5 volts on this side. Now let's give it a whack. Okay, now we're seeing -5 volts, and you know, really -4.8 volts. So it's like I said, now that the impedances match, you know, our charging voltage and discharge voltage happen to be equal. Even though it's got the same amount of energy stored in it, you know, it actually takes longer to discharge it now, even though it's got a smaller resistance. But the reason is that, okay, it had like half an amp flowing through it, right, at 10 ohms. Well, now it's got to have half an amp flowing through it to get rid of that, so it actually takes just as long to discharge it as it does to charge it. But then when we had a higher resistance, like 100 ohms, well, we had that half an amp to charge it, but to discharge it, it's trying to maintain half an amp, but it's having to do that at 100 ohms of resistance instead of 10 ohms. Okay, so because of that, that means, you know, it's got to, you know, its voltage instead of being 5 volts has to be like 50 volts. Okay, but since it's 50 volts, you know, it'll discharge its energy much more quickly, you know, at 50 volts, you know, across a larger load than it would at a smaller, you know, resistance value, just because of the fact that here it can take its time because it's trying to hit the same current mark, but again, it takes more energy for it to go up, clear up to 100, you know, to 50 volts to do it as opposed to 5 volts. So as a result, you see that energy disappear, you know, slower at a lower resistance than a higher resistance. It's real lickety split. And if you go up to 1,000, you know, it disappears real fast, and the voltage goes up to like 500 volts, for example. So it's the opposite of what you might intuitively think, but if you think about it in terms of energy, it makes more sense because of how you're going to have to dissipate things. Now let's change this up to 1,000 microfarads, and let's see what happens now. Now we made this proportionally bigger because this is proportionally smaller. You know, yeah, you're seeing a very interesting response here. So, you know, technically this is a bigger response than we had with the bigger capacitor, but, you know, the larger resistor. Okay, you know, we're down to, you know, the millivolt range, so we're pretty much fully charged. Now let's dump it. Alright, pretty much still a damped response. I mean, you're not seeing much in the way of an oscillation, you know. Like I got when I first started doing this, you know, you were seeing an oscillation. In fact, the voltages were actually quite high. That was at 10 microfarad, but at 1,000 volts, I think. But yeah, you're not seeing much oscillation at all here. Alright, convert it to 1,000 ohms. Let me reset it while I'm at it. I think this is the original conditions. It might have been 100 ohms here. It might have been the next level down. Okay. Yeah, so now you're starting to see an oscillatory waveform here, you know, and here. And you see the voltages are enormous, you know. You see oscillation here and here and here. So anyway, there's that. Now, like I said, we could stick an inductor in here and this thing just kind of freaks out. Well, it freaked out at the values I had in there before anyway. Charged up a lot faster than this with that inductor there. That's interesting. Resistors are all the same. Okay, let's dump it. You see over here it's minus 400 volts, but again, same here. I mean, it produced a really high reverse voltage. See, 490, 460 volts. Even this, you know, you saw a 450 volt spike here. So, yeah, because this is our inductors parameters here. So, you know, it's got 5 volts. It's being nice and behaved when you're charging it up out of a 5-volt battery, but now if you flip it, alright, not so well behaved, but you know, the current just falls through the floor, and you know, and again, you got these large voltage spikes over here, as you can see. So I mean, that's what I'm saying. It's just because, you know, we're taking the same amount of energy and dumping it out into a higher impedance, it actually results in a quicker dump. The higher the resistance, the faster it loses that energy. So now let's just switch over to 100 ohms here. Well, actually, again, okay. Reset it. Alright, so this is with a 10 ohm load, and you'll note that the voltages here are all going to be tame. I mean, there's not, you're going to see any high voltages at all. You know, here's the resistor voltage over here. So but you know, still taking this longer to charge up because now it's got a load on it, so it's eating up some of its energy. That's why the curve is quite a bit different here. So like I said, we dump it, but you still want to see about 5 volts even when it's dumped. Now here, I guess we did still see a big spike. So again, just goes to show you, if these things change state, yeah, you can see some really big voltage spikes. You see this starts to charge up really fast, and at some point it's running into the resistor. So that's probably an artifact of its modeling, I would imagine. So at any rate, let's go up to 1K on this. Reset it. At 1K, these things are actually pretty similar to each other, because that is such a very small load here. I mean, it's, just a milliamp or so. So that 4 volts across the resistor here. This had 4 volts here. And the charging times are similar because the resistor has less impact because it's a large impedance. Sufficiently charged. Alright, let's hit it. Okay, now we get like a 200 volt spike over here. Remember before we weren't getting any kind of high voltage spike, and here we're getting a 400 volt spike, but it's much more drawn out. Instead of being a little chirp, it's now a pretty wide band. So, and again, it's trying to maintain that ½ amp of current, but and here's the same thing. We get this this spike drawn out. This is kind of what happens in a switching power supply right here. They kind of go back and forth. So you can see that the voltages on one side are really unrestrained, but on the other side, they're like nominal. Say 5 volts versus 75 volts. So the faster I switch it, the lower those peaks are. Leave it off here for a minute. See, these are 144 volt spikes, but this side is still only 5 volts, and you get these little current spikes. Of course, that's affecting our inductor over here too. It's kind of behaving the same way, because we're storing a lot of energy in it too at 1 Henry, and then it's releasing it. So you're seeing the fallout from that. So that produced a 19 volt spike because I was switching it fast enough, and certain power supplies work that way. Some switch mode power supplies work that way. The current in the inductor kind of goes down almost to 0, if not 0, from that. But yeah, so in any event, some rather unusual stuff, but it actually gives you an idea, particularly about how you can charge up at well, let me do this now. So now the fields will charge up much more quickly, but we're storing 1/100th the amount of energy in the coil, so that's why it actually charges up more rapidly, even though we made the resistor larger. So you would think it would take longer to charge, but in fact you're storing less energy in it because you made that larger. Remember, in the end, the voltage across these coils is still the same 0 volts. You know, so you take it negative. Okay, now we're only getting like a 24 volt spike here and a 43 volt spike here because, you know, we lowered the ratio of impedances, and that's what's important, is the ratio of impedances. So, you know, if you charge up at a low impedance, you're going to store a lot more energy in the coil, and then if you all of a sudden discharge it into a really high impedance, it's going to produce a very high voltage, but a very short discharge time. In fact, way shorter than your charge time. You know, because the smaller the resistor, the longer it takes to charge, but the more energy you store, and if you dump that into a high impedance, the higher the impedance you dump it into, the quicker it'll discharge, but at a very high voltage. So it's very fascinating, you know, to realize that see, that's what I'm saying, it's why it's so hard to wrap your head around inductors and so forth. You know, and anyway, this sort of mimics, you know, what goes on in certain power supplies, really, because it's you know, but you know, I was well, let's look at this. So, you know, you see you got your 5 volts here. Okay, but you know, you got 24 volts formed when I discharge it. But like I said, these things don't take long at all to charge up. But they only still generate about 24 volts. You know, when I switch it. So, but it is generating a higher voltage than you might think, because these transformers, this is a 1 to 1 to 1, which is interesting. So that makes this a so this is a 2 to 1 transformer then. So well, yeah, so the ratio is 1 to 1. I guess that's for the whole primary versus the whole secondary, so maybe it is just 1 to 1. I was thinking of it in terms of that other transformer they have, the split primaries or whatever. That was 1 to 1 to 1, but I think this is probably just 1 to 1 then. So, but this is usually the primary, and that's usually the secondary, but regardless. But yeah, so at any rate, you know, this still is producing a much higher voltage than technically we're inputting. It's like 5 times higher. So, interestingly enough. So I'm not sure why that is exactly. But I would imagine if we take this down to that level, you're going to see that drastically increase. It takes drastically longer to charge it up now, and you're storing much more energy, and it's got 10 times the amount of current that it's trying to get to. Whereas normally it was charging and discharging like this over here. Down to about 100 millivolts here. Now let's try to flip it. Okay, see, now we're getting like 200, instead of 24 volts, we're getting 240 volts over here, but we're dealing with a lot more energy, you know. So it's like I said, you know, the amount of energy you have stored in the inductor, you know, has a big impact on the actual voltage spike you see. But it's because of the fact that a smaller impedance in this case, you know, in the secondary, you know, again, your primary versus secondary impedance, in this case we're dumping it through this resistor, but it's you know, this 10 to 1 ratio is still applying here, interestingly enough. So you're seeing it there, and you're also seeing it here. Now here, you know, the spike was 430 volts, versus only 240 here, so it's almost twice the voltage here than it was over here, which makes me wonder if this in fact isn't a 1-to-1-to-1 ratio here. I mean, I'm not sure about it. That makes me wonder, because again, I would expect to see kind of the same voltage on both sides, given the fact the impedance is the same on both sides. But it's not, but it does make sense that this would be, 10 turns here, 10 turns here, and then 10 turns here. So, if that's the case, and this has twice the inductance, so yeah, you're going to get half the voltage here. So, that's probably what's going on here. But, in any event, though, the voltage, like I said, is much, much higher now because we used a higher impedance, and again, we got, we kept the impedance the same, but we used a lower impedance and are storing more energy in there, so. Got the same deal, if I switch it fast enough, it still is only outputting about 20 volts, 23 volts. It's only about 12 volts now, despite the fact I increased the impedance a lot. Impedance went up by 10 times, which means it's storing much less energy in there, but we're still getting pretty big voltages out for roughly the same kind of duty cycle. See, it's coming out about 50 hertz every time. So, whereas you can see over here I hadn't changed anything, but we're getting like 31 volts, minus 31 volts, and over here we're getting like 28 volt spikes on the secondary, and again only 4 volt here. So, but in any event, that's what I'm saying. The bigger we make our input impedance, the less energy we store, and the less energy you're going to see there. So, right up until they're equal, and see, now the spikes are hardly, they're quite negligible. On both primary side and the secondary side, they're quite negligible. 4 volts here and 2 volts here. So, again, it's how much energy you put into the inductor has a large, plays a large part in it. But yeah, these inductors, you got to be aware of that anytime you're dealing with inductors in a circuit, there's always a potential, if you don't watch what's going on, there's always a potential for it to produce really high voltages. So, anyway.